In this video, we are going to be doing some Chapter 1 review problems. So in this video specifically, we are going to focus on problems that involve solutions to systems of equations as well as the concept of linearly independent vectors. Okay, so first let's just review. What does it mean when we say vectors are linearly independent, and what does it mean when we say they are linearly dependent? So if I have a set of vectors, v1, v2 up until vk, we say that those vectors are linearly independent if, when we form a linear combination of them that equals the zero vector, so if I write c1 v1 plus c2 v2 plus dot 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 plus ck vk and it equals 0, if that only has the solution where all of the c's equal 0. Because that's clearly one of the answers. If I plug in 0 for all of these weights, that's clearly going to make it be equal to 0. But if that's the only one, if that's the only solution, then we say the vectors are linearly independent. Okay, all right, let me just write that 0 a little better. So this solution where you let all the weights be 0, that's called the trivial solution. Okay, if I were to express this linear combination in matrix form, I would get a matrix where we have those vectors v1 up until vk written as the columns. So maybe I'll call that matrix A. And that gets multiplied by a vector where we take all the weights and they are the entries of the vector. So I'll call that x. Okay, so another way to say this is that if I have linearly independent columns, if v1 up until vk are linearly independent, well, that would mean that the only solution to this equation is when all of these entries are 0. So linearly independent columns means that's equivalent to saying, well, the only solution to ax equals 0 is x equals 0. It only has the trivial solution. Okay. On the flip side, if there is a non-trivial solution, so if there's something where not all of these ci's have to be 0, so where not all of the ci's equal 0, then we say that the vectors are linearly dependent. Okay, all right, so that's just a review of those definitions. Let's do a practice problem. So this is coming from worksheet 3, problem number 2. So this is a practice problem that would be good practice for both standard S8 and standard S6. And it says, suppose that the vector 1, 2, 3 is a solution of ax equals b, and the vector negative 2, 0, 4 is a solution of the homogeneous equation, ax equals 0. Part A says, or asks, are the columns of A linearly independent? Justify your answer. Okay, so I first want to, and then part B says, write two other solutions of the non-homogeneous equation ax equals b. I first want to give you an opportunity to try this problem. So pause the video for about 2 minutes and try just part A. Focus on part A first. 4, 3, 2, 1. Pause it for 2 minutes and try A. All right, so hopefully you did that. Hopefully paused it for about 2 minutes to try part A. Let's talk about it now. Let's talk about it together. So it asks, are the columns of A linearly independent? So one of the things that makes this problem hard is we don't know what the matrix A is. So how can we answer this question? Well, the problem tells us this piece of information about the equation ax equals 0. And that reminds me of something from the definition of linear independence above. Okay, so if negative 2, 0, 4 is a solution of ax equals 0, that means if I plug it in for x, if I do a times negative 2, 0, 4, it's going to work. It's going to make that be equal to 0. Okay, well, if I were to write A in terms of its column vectors, well, because I'm multiplying it by a vector that has 3 entries, for that to work out, A needs to have 3 columns, A1, A2, and A3. So now when I multiply that matrix by that vector, I get a linear combination of those columns. It's the first entry, negative 2, times the first column, A1, and then plus the next entry, 0, times the second column, A2, and then plus the third entry, 4, times that third column, A3. And that needs to be equal to what I have on this side. Okay, so that is one of the ways that we multiply a matrix times a vector. You get a linear combination of its columns. Okay, but what I have here is, if I refer back to my definition for linear independence, I have a linear combination of these A vectors. It equals 0. And these weights, well, they are not all 0. Okay, the weights are not all 0. So because of that, the vectors are linearly dependent. I'm going to write, just to abbreviate that, I'm going to write LD to denote linearly dependent. Okay, nice, and that is my answer. So I didn't even need to know the columns of A. Using this piece of information by itself, we were able to determine that the columns were linearly dependent. Okay, I just want to mention that there's another way I could have solved this. So let me call this solution 1. Solution 2 is to return to, this fact right here. If I have a matrix, its columns are linearly independent if the only solution to the homogeneous equation, Ax equals 0, is the 0 vector, if that's the only solution. But based on what I have here, based on the fact that A times -2, 0, 4 happens to be equal to 0, well, this means that the equation Ax equals 0 has a non-trivial solution. It's got a non-trivial solution. There's a solution that's not just the 0 vector multiplying my matrix. Okay, so that means the columns of A are linearly dependent. Okay, so that's another way I could have argued this. I like the first solution maybe a little bit more because it's a little bit more descriptive, and I can more clearly see that, oh, there's this linear combination where not all the weights are 0 that happens to be equal to 0. Okay, all right, let's try part B. Part B says write 2 other solutions to Ax equals b. So I first want to let you all try this. So pause the video for 2 minutes and try this on your own first. 4, 3, 2, 1. Pause it for 2 minutes and try it first. Okay, so hopefully you did that. Hopefully you paused it and tried it for about 2 minutes. Let's talk about this one together. So this one involves a key theorem back from, I think section 1.5, about how the solution to Ax equals b, the non-homogeneous equation, compares to the solution to the homogeneous equation, Ax equals 0. So recall that the solutions to Ax equals b, a non-homogeneous equation, they have the following form. They look like x, my solution vector x, it has the form p plus vh. And I'll remind us what both of those things mean. So this vector p is a particular solution to Ax equals b. The word particular just means it's one solution. So p is one solution to the equation Ax equals b. There may be many solutions to that equation, but p is just one of those solutions. And then vh, the h represents the fact that it's talking about homogeneous. Vh is a solution of the homogeneous equation, Ax equals 0. Okay, so based on what's given to us in the problem, well, we know one of the solutions to the homogeneous equation. It is this vector -2, 0, 4. Okay, so we know that -2, 0, 4 is a solution to the equation Ax equals 0, to that homogeneous equation. Okay. So, and we also have p. We have a particular solution to Ax equals b. The problem tells us that as well. It's this vector 1, 2, 3. Okay, so we can also say that, let's let P be the vector 1, 2, 3. Okay, so my goal is to get 2 new solutions to the homogeneous equation. So, okay, I think we're ready to at least write down 1 new answer. So my solutions to ax equals b, they will look like p plus something. So p is 1, 2, 3. 1, 2, 3 plus, and then I have to be adding a solution of ax equals 0 to it. Well, I know one solution to ax equals 0. I could take the vector negative 2, 0, 4. And I could add these together. I could add these together, and I'll get negative 1, 2, 7. Okay, so nice. So we got 1 new solution to ax equals b. But the problem said, well, let's get 2. So we need another one. All right, so how could I get another one? Here's one answer. Let me box this thing. So I need another answer. So it turns out that if I have 1 solution to ax equals 0, this vector negative 2, 0, 4, if I were to now, like for example, multiply both sides by a constant. If I were to multiply both sides by a constant, let me call it c, ax, and then multiply that on the right as well, c times 0. So, well, something times 0 is just the 0 vector. And on the left-hand side, I can pull the constant inside. That's one of the properties of a linear transformation. So that'll give me a times cx. So one of the things that means is if I have 1 solution to the equation ax equals 0, well, if I multiply that vector by any constant, well, that will still give me the 0 vector out. So because of that, any multiple of negative 2, 0, 4 is also a solution to ax equals 0. Oh, because that is very nice. So, well, let's just take an example. So, well, let's write p. The particular solution was still the vector 1, 2, 3. And now I'm going to add to it another possible choice for that vector vh. So let's multiply this vector negative 2, 0, 4 by some constant. Maybe I'll multiply it by 2, and that'll give me negative 4, 0, 8. And if I add those together, we'll get, what is it, negative 3, 2, 11. And we got it. We got our answer. All right.